just cannot run in kernel mode on a hypervisor environment. For example, these instructions here taken out of, I think, macOS 10, load some privileged registers of the system. On a real system, this in kernel mode, this can of course happen, but not if you run all this in user mode or if you run this as unprivileged code. So what happens is with this LGDT, you get a trap. So the system goes into kernel mode, and the hypervisor can then emulate it with some pseudo C code here. The same is true with the next instruction. The third instruction is actually one that doesn't need any privileged accesses. That's just some calculation. It can just be executed. The next few also trap again. Yeah, so this is the interface between the operating system now in user mode and the hypervisor in kernel mode. But what about our processes? These processes think that they are in user mode, and they are, and they think the operating system is in kernel mode, but it isn't. So if a process with its kernel interface wants to connect to the kernel interface of the operating system, it doesn't work directly because it wants to talk to kernel mode, but the operating system is running in user mode. So what is done here is a trampoline approach, so that every call gets intercepted. Well, anything that user mode wants to do with kernel mode will not go into the operating system, but will always automatically go to the virtual machine monitor, which will then detect what the operating system, what the process had in mind, and can dispatch this call to the kernel interface of the virtualized operating system. Whoa, this isn't supposed to be there. So what are the components, for example, of a VMware system? You have two components. One is running in user mode, which is the VMware executable, for example. And in kernel mode, you have another support kernel module, which is needed. The VMware main executable does all of the main logic. It does all the high-level emulation, like device emulation and boot up and BIOS devices, all these things. And you need kernel mode for all the mode switches. Kernel mode, user mode, mode switches, all that. You'll see that on the next slide. And also to intercept all the interrupts. All these things that just cannot be done in user mode must be done by a kernel module. Because if you have a virtualization system that runs on Linux, you have to put the kernel module under the GPL. Therefore, VMware and all the others try to put as much code as possible into the main logic in user mode, which they don't have to open source. So you cannot see all the interesting parts in that kernel module. So it only does what is really, really necessary. So let's have a look at scheduling again. We have these two parts, the VMware executable and the kernel module. Let's start with a big view of the complete system. The VMware binary gets a time slice. Time interrupts occurs, scheduler, another process gets run, the operating system scheduler, well, this is the scheduler of the base operating system or the hypervisor. In this case, what I'm telling here is that you run VMware on, for example, Linux, and not the VMware server thing, which has its own operating system. So this base operating system on which VMware would run has two processes here, VMware and a process 2, and schedules between these two. So each of them gets about 50% of the CPU. Now let's zoom in. What exactly happens if you run this VMware inside this VMware time slice? First, the VMware user mode binary will be run. It then switches into the guest code, so it donates it's almost the complete time slice for the guest code. And when a timer interrupt occurs, there's another switch back to VMware. All these switches are called world switches. So let's zoom in some more. At the start of a time slice, the user mode binary, VMware gets run in user mode. in user mode, you cannot do a world switch, because a world switch would mean you change all the registers, you change all the memory layout, you change, you replace your scheduler, all that. So you have to do that in kernel mode. So the user mode binary switches into the vmmon kernel module, which can then do the world switch, run the guest code. For example, now it's user mode code. Let's say you have, now that's a Windows application that is running for one time slice on the hypervisor running on a Linux system. So this is user mode code also running in real user mode on the machine. Then, for example, this application wants to make a syscall. This syscall will be intercepted by something in kernel mode. So we have another world switch. The vmmon kernel module will intercept this, will switch up to user mode into the big VMware binary, which has all the logic, and will decide what this was. Was it a syscall? Was it an interrupt? It will then decide and do what it thinks is right and switch back into vmmon in this case, because we have to switch into virtualized kernel mode for the syscall. So there will be another world switch by vmmon into guest code. Guest code is always run in user mode. And this time it is, for example, Windows kernel code, which is supposed to do something with the syscall. If the Windows kernel code does a sysret, returns from the syscall, we have yet another world switch into the kernel module. Kernel module will then hand all this up to user mode, which will hand it down again, do another world switch, and we are in the guest code again, in user mode, in our Windows application. So let's say at the end of this time slice, we have another time interrupt, which is supposed to run the base operating system scheduler again. This will again result in a world switch. Kernel module will hand it up, and it will in the end be handed to the system scheduler, which means the end of our time slice. So the whole idea of this donating a complete time slice to the guest looks a lot like with these world switches, you completely change the mode of execution. You change your complete world. That's why it's called a world switch. You get a time slice. You have to change everything to run something else which is completely incompatible, has a completely different memory layout. But at the very end, when there is a timer interrupt, you have to clean up, because the original operating system on which you're running has no idea about this virtualization thing. So this is like when your parents are gone and you want to have a party. Just when the bell rings, you have to clean up. So you have to intercept the bell, and you must make sure that your little brother doesn't intercept the bell and have them come in. So that is why we intercept the timer interrupt, or VMware does, with its kernel module. Let's zoom in some more. So what does a world switch look like? The world switch has to change really everything of the CPU. The register set, of course, because, well, that's mostly how it works with threads and processes on any operating system. Every process has its own register set, so we have to switch the register sets, including the interrupt vectors, so that the interrupts do not get intercepted anymore by the host operating system, but by vmmon. And also the page tables have to be changed, because the memory layout of the guest can be completely different. So what does virtual memory inside the guest look like? So this is something just how it typically looks like. This is not something that virtualization imposes on how guest mode works, but typically you have some application code and application data at the bottom of memory, and at the top you have your operating system. So the interrupt vectors typically on a normal system point to some code in the operating system, but with virtualization we have to intercept the interrupts and not the guest operating system. The guest operating system cannot run in kernel mode. It could not intercept interrupts. That wouldn't work. Therefore, we add some page somewhere, some small page, and direct all our interrupt vectors there in our VMM code. We just map it inside the guest's in the guest's address space, so that we can do all these interceptions. So normally when you have a time interrupt at the end of a time slice, the scheduler would run, but in this case this just wouldn't work because we have completely switched worlds. Everything is completely different. The host operating system would have no chance to work because all the page tables are changed, all the interrupt vectors are changed, all the registers are not what it thinks they are. So it would just crash. Therefore, we have to intercept it with VMMon, do a world switch, go up into user mode, and now everything's back to normal. And the operating system, the host operating system, doesn't even notice that we have done so much. At the time slice start, it started some user mode program, and at the end of the time slice, we're back in the user mode program. So we can just let the scheduler run. Also, now this is a complicated one. You see, if you have, in this example, we have two operating systems with two applications each. If you only look at the left side of the slide, you have two address spaces, two processes on one operating system with their mappings. The second operating system also has mappings of memory into what it thinks is physical memory. So the operating system doesn't know about virtualization. It maps its guests' pages into what it thinks is physical memory. But of course, there's just one physical memory, and the operating system would all use the same pages. So we need another mapping between pages. This is what the hypervisor does. So every time the operating system, the virtualized operating system kernel, wants to do a page table mapping, it also gets intercepted and translated to the effective mapping, and all the page tables get updated to show the resulting mapping and not the intended mapping of the original operating system. But still, the operating system and user mode inside the virtualization will see the correct pages. So what about I/O accesses? This slide is supposed to build. It doesn't. Too bad. But I think you get the point here that if guest mode wants to do an I/O read, it also gets intercepted, because this is obviously kernel mode, because, well, on most systems only kernel mode can do I/O accesses. So this I/O access will also trap into the hypervisor. So a world switch will be done into VMMon, which will hand all this up into user mode again, which will then decide what is going to happen and provide some fake result. For example, if this I/O read was the PS2 mouse device, and what about the mouse? Is there any change about the mouse? So it does an I/O read, and then VMware can fake this input. It can ask the host operating system, has the mouse really changed, has it moved? Put all this together in a PS2 protocol and hand this packet down into VMMon, and VMMon will then hand it into the guest mode code, into the kernel of the virtualized operating system. So this is the theory. Now, how does it work on x86 on practice? Does it all work this way? So I've shown you two different approaches. One is with 3 different layers. For example, the G5 does it like that, or 2 different layers. Most other systems do it like that. So how does x86 do it? Do we have 3 layers or do we have 2 layers? And the answer is no. For example, there's this one instruction which can read whether we are in protected mode or in real mode. Normally, it should trap so that our VMM in kernel mode can emulate it somehow. But on x86, it doesn't. It just behaves differently. So if we have an instruction which is supposed to run in kernel mode, and we run it in user mode, and it traps, that's fine. We can emulate it, we can hand a faked result back. If it doesn't trap and just does something different, we can do nothing about it. And so effectively, kernel mode code might not work. So in practice, it also doesn't. If you try to run a Windows kernel or a Linux kernel without any change in user mode and fake the results with traps, it doesn't work. So what can we do about it? you've seen products like PowerPC or Virtual PC for Mac. They do emulation. You could always just emulate it. So every Turing-complete machine can emulate any other Turing-complete machine. You can have one big loop that